so today Prakhar is going to talk about extending the continuum theory to molecular theory of rods. Okay, Prakhar.
Good morning, everyone. I'll be talking about today on modeling of continuum and nanorods using molecular approach. So, till now in the class we have learned that the strain energy density function for a rod, strain energy density per unit of undeformed length for a rod can be expressed as the integration over the cross section of the rod of the strain energy density of 3D continuum, where F is we have learned that it is e to power sk V tensor product E3 plus kappa cross x naught tensor product E3 plus del x naught over del x alpha tensor product E alpha. And here we have that x naught as our warping function, which is the unknown, and this can be found out using the equilibrium equations that we derived as grad alpha dot p plus kappa cross p E3 is equal to rho naught lambda plus m delta, which is valid through the cross section, and Pm is equal to 0, that's a traction free boundary condition. And then to make this as a uniform strain condition, you need to minimize the energy with respect to strain as well, with respect to the constraints. So you have to solve these equations as well, so that the centroid of the cross section is at origin and you preserve the average sense of orientation of a cross section. So you see that in the deformation gradient, the x naught, that's your warping function, is basically unknown, and to find out you use these equilibrium equations from which you find out x naught. Once you find out the x naught, you find out f. Okay, so once you found out f, then you plug in the f in this strain energy density function, then you integrate over the cross section and you will get the strain energy density of per unit undeformed length for a rod. Okay, now what if you do not know W of f? What's the form of it if you do not know? That's the one question. Okay, and what if rod is not a 3D continuum? So what the question is, you do not know the form of W of f, and that you do not know, and the other question would be that if it is not a 3D continuum. So for example, you have a rod which has a very small radius, so radius of a nanoscale. So what happens in that is, you have a cross section at a nano level, okay? So then the energy of psi Vk would not be simply this, the integration over the cross section, strain energy density integrated over the cross section, but you will have some additional terms due to the surface effects. Due to the surface, you'll have some additional effect. So that's something These are the surface strains. These are the surface strains. And this is the one condition. Then the rod, then the strain energy density you see is not depending on only the bulk, but the effect of surface is also dominating there. So that's a surface energy. Okay. Now this is the one condition. The other could be a hollow tube at a very nano scale. So this is like this one was like a tube. This one is a rod which is carved out from your bulk crystal. So you have a bulk crystal and you take out a rod of nanoscale size. Okay, the radius is very small. So you see that at the top layer of the surface there won't be any atoms. So the top layer of the surface, the atoms at the top layer won't be interacting with the other atoms because it's free. So that's why the elasticity for the surface would be different, and that's why this phi of S has been added here. Okay. So other would be a hollow tube, for example, at nanoscale, or any tube at nanoscale. So for example, if I have single wall carbon nanotube that do not have surface effect kind of thing, these are the tubes produced at a nanoscale level. So for that we cannot recourse to 3D elasticity. If we start modeling these structures with the 3D elasticity, for example this hollow tube, that we cannot recourse to the 3D elasticity, then we have to work and think of a direct approach. So to evaluate psi of V and K, we have to think of some direct approach. And this we will be learning later on as a helical Cauchy-Born rule. But in today's class, my motive will be to evaluate this strain energy density function for the bulk using molecular mechanics or molecular approach. Of course, this part can also be evaluated using molecular approach. There is something extra called surface Cauchy-Born rule. But for this, I'll be using the Cauchy-Born rule to evaluate this. So in order to evaluate this W of F, you have plenty of approaches. The approach could be one is you go for experiments. Okay. So for example, you have an isotropic material, you have only two constants, then you can have the extension and torsion test to evaluate those two constants. Other one is molecular approach, which I will be talking today. That's this Cauchy-Born rule. So the idea here would be you have a continuum rod. Okay. So you have a continuum rod, you strain that rod. And what you see at the atomic level, you see that the atoms are deforming. I mean, not deforming, atoms are moving. Okay. So whatever strain you apply at the continuum level, at the atomic level, you see that there is a movement of atoms, and that is determined by the help of the bond energy between the atoms. So that's the energy of the atoms which determines the movement of these atoms. But for that, what we require first is how the atoms are arranged in the continuum rod. ऐसे कर दो. So we need to look at the arrangement of atoms, okay, at the nanoscale level. So here I will focus on crystalline materials. So what's so special about the crystalline materials is they have their translational periodicity in them. What is that? I mean, they have a regular arrangement of atoms. So for example, if I have these are my atoms, okay? This length and this length is same, okay? So you see that every atom has the same environment. If I look to this atom has same environment. If I look to this atom also has the same environment. Okay? So they have a translational periodicity in them. So the crystalline materials has translational periodicity. That means if I translate this here and translate this there, you see that I am able to form a crystal. Okay? Now what is, if you want to generate this crystal, what you need is two things you need it. So to generate a crystal, you need lattice vectors and the basis atom. So through the lattice vectors, you generate the lattice, okay, and the basis atom is the number of atoms per lattice point. Okay, so if I take example of this 2D lattice only, so I have AE1, AE2 as my lattice vector, okay, so that's my capital A1 and that's my capital A2, okay, and if I use a formula for generating this as small x is Ni AI plus xj, where j is 1 to m, where m is these are the basis atom, okay, and these are the lattice vectors which you translate via integer number, that Ni belongs to the integer.
I think on the left hand side big X,
Yes sir.
you could use a subscript, isn't it? I1, I2, I3, comma j for big X.
Okay. Yeah, this is a I1, I2, I3. This is inside this n.
Or you could write N1 and N2.
Exactly, yeah. So via this we generate the lattice, and this is our basis atom. We put these atoms on the lattice, and together with that we form a crystal. So I will take an example of a simple cubic. Okay, I'll just take the example of this one as well here. So what you see is, as I said, I need to generate this crystal. So first of all, I generate the lattice points for that. So I have AE1, AE2. I set my origin somewhere here. So that's my AE1, that's the first one, and that's AE2. And I've put my basis atom, and now basis atom I'm saying that this is a lattice vector, and basis atom I'm saying it as 0, 0, 0. So I put this basis atom over here. Okay. So this is this while, and then you translate this here by 1. So that is AE1. If you go there, plus the basis, and N2 will be 0 for here. For here it is 0 comma 0. If I see N1 and N2, if I write N1 and N2, so this is my N1, this is my N2. So that's 0 comma 0, and then it is 1 comma 0. Okay, and then I take my lattice vector here, and then I put this atom over here. So for this point, if I say for atom B, if I'm talking about, the XB is actually AE1 plus 0 times AE2 plus 0 E1 plus 0 E2. This is the basis atom, this is for the basis atom, and this is for the lattice point. So through this I first prepare my lattice point, and then on that I put my atom. Okay.
So M is the number of atoms?
Yes.
The lattice
Yes, yes. So I'll take another example for that.
Is AE1 plus XB, is this expression the right hand side XB, or is it XB, or is it AE1 plus?
This?
Yeah, and above there is
Oh,
A1 plus.
this is nothing.
Okay.
Take another example of body center cubic crystal. In that case, our lattice vector is AE1, AE2 and AE3. So that generates the lattice points, and now I have to put the atoms inside that lattice point. Okay, so I have my basis atom, because BCC contains 2 atoms, 2 basis atoms, so it's a 0 comma 0 comma 0 and A by 2 E1 plus E2 plus E3. Then I look towards this map again. So at the first point I generate first the lattice point from there. So my origin is somewhere here. Okay. So if I put N1, N2, N3 as 0, 0, 0, and the basis atom here, the M, if you look, M is 2. M is 2 here because there are 2 basis atoms. Okay. So I put first, I make a lattice point here from 0, 0, 0, 0. So that's this point. Okay. And then I put my first atom 0 comma 0 comma 0 over that. So this is one atom. Okay. Now the next is we need to put the others, the second atom. The second atom is half of this distance, half E1. So this is my, so this is E2, this is E1. So if I go A by 2 E2 in this direction, and A by 2 E1 in this direction, and A by 2 in E3 direction, so I'll form an atom here. Okay. Okay. And this one. Okay. Now again translate this. If I translate this in this direction, I'll form this atom here, with similar procedure. Okay, and similarly, if I translate here in this direction with only one basis atom there, I'll form this. Similarly for this. And you get again an atom here. So you just see that, if you see that small cube, if you translate this in this direction, translate in this direction, translate in this direction, you'll form a whole 3D crystal from that. And that's what is a translational periodicity. You have a small unit cell. This is your unit cell, smallest unit cell. So that's the smallest unit cell you have. And when you translate this in this direction, in even direction, similarly in E2 direction, similarly in E3 direction, using that kinematic, that map, you'll form a whole crystal. And that's what is a translation periodicity which I'm talking about. So till now, you have position of atoms. So you have the position of atoms, and with the help, with the position of these atoms, you have the bond energy, bond length. And when you put this bond length in some energy form, you'll get the energy between the atoms. Okay. But look at the continuum picture for this now. We'll look at continuum picture for this. So this is the crystal that is formed in the undeformed state. Okay, so there is no deformation that I have applied. So if I look my body and I deform it via F, and it deforms something, then if I look, if the crystal orientation is like this, I find that at the nanoscale, the variation of this F is very slow. Thus, it appears to be homogeneous. Okay, so that deforms homogeneously, and the periodicity is maintained. So the periodicity is maintained after deformation. So if you have a lattice vector A1, A2, and it deforms some, capital A1, capital A2, that's the undeformed lattice vector, and it deforms to a lattice vector A1, A2, then through the continuum mechanics knowledge we know that this can be mapped as A1 is F times capital A1, similarly A2 F A2.
Could you explain why it remains periodic, a small part of the crystal layer, when you apply any arbitrary deformation gradient? Why does it still remain periodic?
So the periodicity is due to the fact that when the deformation is applied at the large scale, if you look at the nanoscale, what happens is the deformation gradient, the F, appears to be changes very slowly. So it appears that the crystal deforms uniformly. In a small region, if you look, you will find that the crystal structure is almost the same throughout. Okay. So let's have one more example to understand this map. Suppose I have a rod, continuum rod. And my deformed coordinate are such that small x1 is capital X1, small x2 is capital X2, but small x3 is lambda times x3. So can you see what is happening here with this deformation? Yeah, it's a stretching by lambda. Okay, so if I stretch my rod in this direction by lambda, and I look at the atomic level and take out a unit cell from it. Okay. So if I take out a small unit cell, and if it has a unit cell, so if it has a side length A, not to use A, B. So what will be happening after the deformation when you apply this map? What will be happening to this length?
Lambda B.
Exactly. So at unit, so you see that what the map you applied at the continuum level is valid there as well. Therefore, you see that A3 is nothing but lambda B A3, lambda times A3. So you see that this map AI is F times AI is valid here, and this map is actually called as Cauchy-Bonn rule, which relates the deformed lattice vectors with the undeformed lattice vector. So this is basically bridges the atomistic and continuum. Via this map.
What about this relative position vectors?
Exactly. So
The basis atoms?
yes, that I'll discuss now. Yeah. So as you see that only we have found that how this lattice vectors deforms when the deformation is applied. But what about if they have the basis atoms here as well? So how does they deform it? Okay, so that's the unknown. So they deform via this map. So J is your basis atom. J runs to 1, 2, 3, 1, 2, and so on, M till M. So J runs from 1 to M. So when you apply the deformation, you have this F as known to you. But this is something, the position of the basis atom is unknown to you. So this can be found out by minimizing the energy of the unit cell. Okay? And using this, so you will get the deformation map that says about the interaction within the unit cell and across the unit cell. And finally, you can evaluate your W of F as by minimizing the energy, unit cell energy, which depends on the basis atoms x1, x2, xm. When you apply the deformation, minus the energy of the unit cell when it is undeformed. Over the volume of the unit cell. Okay, so this is my strain energy density, and I minimize this with respect to the positions, deformed positions. So I'll get my x deformed positions from this by minimizing this. So for a given, as to how to evaluate this unit cell energy. Okay, so for that we should know some interatomic potential for that. So we need to know the interatomic potential, which determines the energy between the bonds. Okay, so I take a very simple example of pair potential. So what happens in this is an atom is affected only by another atom. So a pair, so the energy of this bond is because of the two atoms. Okay, there can be, so that's a pair. This is one pair. This can happen that this atom is also affected by the another atom. So that's a triad. Three atoms. So that's a 3-body potential. So this is a pair potential in which you count for individual energy of bond pairs. Okay. So one of the example is LJ potential, Lennard-Jones potential, where the bond energy is actually the function of the bond length R, which has some form like this. So with this bond, so once you had the bond energy, the bond length is, yeah. So this phi of R goes like this. So as the bond length increases, the interaction decreases and the energy goes towards 0. So yeah. So now the question is how to.
We can also show the meaning of epsilon sigma in that diagram. Which is what? But one is the potential gas.
Yes. One is the and for energy, the other one determines the minimum R. So maybe from here.
This one?
So there are two parameters. One is what's the epsilon and sigma are the two parameters which somehow tells you the height of the well or the depth of the well at the minimum energy. And
So
the other one.
So if sigma is R, potential is 0, so that gives you the distance for the potential is 0, right?
Yeah, if sigma is R.
Or if R is sigma, let's say.
Yeah, if R is sigma, then
Then you have that
That's
point
right.
that it crosses the horizontal axis.
This one.
exactly. Yes.
Isn't it?
Yeah.
So that's the distance sigma.
Mm-hmm.
And I think epsilon is the depth of the well.
Yeah, maybe if you differentiate, you can find out what would be the R for the minimum energy. It's not hard, is it? But somehow it's related to the depth of the well, epsilon.
So now I'll evaluate the energy of a unit cell. Okay, so I'll take an example of a 2D lattice. So you see, this is the smallest unit cell you have. If you translate this in this direction you generate the whole crystal like this. Okay. So the idea here is to
What are the basis atoms? What are the lattice vectors?
So-
one more time.
Okay. So here the lattice vectors are these. These are my lattice vectors, and these are my basis atoms.
So we will draw the arrow first basis atom.
So these are my two basis atoms.
So they are the position vectors of the two basis atoms.
So if I want to write the energy of this unit cell, of this smallest unit cell, so I'll write E is half of summation alpha summation beta phi r alpha beta. So where alpha is the basis atom, and here if you look is 1 and 2. So only you have two basis atoms here. So alpha runs from 1 to 2. Beta is the neighbor. Beta is actually the neighbor of the basis atom. So for example, if I call this
Beta is the neighbor of alpha. Right?
exactly here. So if I call this as my alpha, then rest all will be the beta for it. So those are neighbors of this basis atom. And you see that I have accounted the bond length between them. So if I have the neighbor, for example, this alpha is neighbor of this beta, then this is my R alpha beta. Okay, so that's the bond energy I am accounting here. So this summation will run for one for the first basis atom, and it will again run for this second basis atom. Okay, and what happens is when you run for this basis atom, for example,
So could you, for example, with green or maybe with red, draw the neighbors of red basis atom? Those red arrows, those red bonds, draw the all bonds for the first basis atom. Yeah. Very good.
no.
So that's what we'll talk about. And then for the blue one, draw all the with blue.
So yeah.
So basically, we have two summations here, alpha, beta. The first summation alpha is for all the basis atoms, and beta is for all the neighboring atoms
Of alpha.
So therefore, the double summation is actually running over all the bonds. Then isn't it? First for alpha, then for beta. And then the question is, how many neighbors to take? Isn't it? Because there is no end to it. You can take as many neighbors as you want. But
So why do you have the orange and the blue arrows?
So
Say for that particular alpha atom,
yes. So
we also have to run over all the blue atoms, right?
So these are the, for this alpha, the red bonds are describing that these are the neighbors of it. Just to show a picture, that these are neighbors of it.
Yeah, but we also have the interaction with blue atoms, no?
Exactly. So blue atoms with this, and I have twice this thing.
Yeah, but I mean, if I'm at that particular alpha, I'll visit all the other orange and all the other blue.
Yes.
yes.
Yes. Yes. Yes.
All those. So can you now tell about which ones actually you did it? How do you decide that?
So that is decided by the cutoff radius. Okay.
Yes, maybe you can draw a cutoff radius.
So if I have this atom and so this is affected. So for example, this atom is affected only by these atoms which is present inside the cutoff radius of this atom.
And for the blue one, you have different circle. Right?
Different circle.
Can you draw that? With the blue circle. And the green one, please do that with red one.
Do you actually distinguish between bonded and non-bonded interactions? So these are not only chemical bonds where atoms interact with each other, or are they only chemical bonds?
It's the energy basically, the bond energy, which is the bonds interacting with them.
By non-bonded, you mean ion bonds?
Ionic bonds.
Yeah.
So it all depends on your potential model.
Exactly.
Okay.
And then, for that, it's just the potential model, and whether it is bonded or non-bonded, they all are dictated by whether it is coming within that R cutoff.
Okay.
Yes.
Okay. So you do not distinguish between
Bonded and non-
neighbored atoms, which have only only the next neighbors in a lattice, and those far away from that.
Exactly.
Okay.
We do not distinguish.
Yeah.
It may be that the potential model
Yeah.
is different for the immediate neighbor and something else for very far away.
Yeah. Okay.
But if you can have a single potential model, then you do not distinguish.
Okay. Thank you.
So the last thing is that if you look that when I take this as atom alpha and I account for the neighbors, I find that this is my neighbor, for example, okay? And when this becomes alpha, this finds that this is its neighbor. So this bond is coming twice into picture. This. So that's why you need to divide by 1/2 so that you only accommodate those bonds which are present inside the unit cell or crossing the unit cell. Okay? So when I write this energy of this unit cell, I want to write the energy for all those bonds which are present inside the unit cell or crossing the unit cell. So for example, if I look to this bond, So if I look this bond, this is the neighbor of this. This atom is neighbor of this atom. So I count this bond. Similarly, when this becomes alpha, this is the neighbor of atom is this. But you see, both these bonds are same. Okay, so these bonds are counted twice. That means so once I count this, divide by half, I will get the energy of this bond plus this bond inside that. So for example,
You have to be more clear.
yeah. So for example, if this bond length till here is A, okay, and till this it is B, then if you look here, then this to this is similar to this. So I'll write A here, and from here to there is B. Okay. So if I when I make it the neighbors of it, so I'll get twice of A plus B. Isn't it? That's why I need to divide by half, so that I only account this energy and this energy. Because that is the bond, the crossing bond which is present in this unit cell. Only this bond affects the energy of this unit cell.
So basically, when we compute the unit cell energy, we either compute the energy of the bonds which are completely within the unit cell, and then we get its full energy. And for bonds which are partially within the unit cell, then you only have to take the partial energy of those bonds. Because the part of the bond which is outside the unit cell would not count as energy for the unit cell. We only take the partial energy for bonds which are crossing. But if you look at the summation there, we don't really have the partial summation. We are taking the full energy, right, for every bond. But that half thing actually works in a nice fashion that, as Prakash was explaining here, you have two bonds here. One bond has got length A within the unit cell, the other bond has got length B in the unit cell. So together it is the full bond within the unit cell. But in the summation you are counting both of them. But since only one is present, as a whole just one bond is present, so that we divide by 2.
Does it half depend on number of bases items?
No, it does not. You can have as many basis items as you want, but magically this half will always work. It's not so magic, it's because of the periodicity. I mean, if you just look at it, it looks like magic. When you work it out in detail, you see that it is because of the periodicity of the atoms. That is half takes care of that partial bond energy. And it's not just for the, there are many other complicated potentials. This was a very simple pair potential when you identify energy using bonds. But there are many energy models where it's a 3-body potential or 4-body potential, or there is complicated bond order potential. But even there, this half works. Yeah. And you can actually prove it mathematically that yes, it's going to work. Yes.
Explain about the cutoff radius.
Yes, Prakash, can you explain how we determine the cutoff radius?
So one of the way to determine is, as you see that if you look to this figure, as the radius of interaction increases, you see that your energy goes to 0. Okay. So suppose, for example, of course you can take the neighbor. For example, if for this atom, you can take the neighbor as this atom here somewhere. But you will find, based on your potential, you will find that the amount of this is actually 0. The amount of energy, it is less. Exactly. It comparatively less with those atoms.
So this potential is basically the van der Waals bond, or
So these are the van der Waals bonds, and depends on how, I mean, what kind of model you are using it. It can be ionic as well, or the covalent bond simple. Okay, so this was the basic, very simple example that I took for pair potential.
often the cutoff is such that an atom interacts only with the neighboring atoms. Often, in case of covalent bonds, but when you have ionic bonds, because then the interaction is really strong, then one atom can interact even with an atom far away. So in those cases, the cutoff length is large. But usually for covalent bonds, for example, carbon-based atoms like carbon nanotube or graphene, the cutoff is such that an atom interacts only with its neighboring atom. But it's not necessary for the general model. It's not necessary that it only interacts with the neighboring atom.
For example, is the Coulomb interaction. If you charged, say, particles,
Yeah.
then there is no cutoff here.
Yeah.
No range induction.
It's not as strong.
May I ask, how do you distinguish between the distance vector r alpha beta within the cell and the distance vector that reaches from this blue to the red one across the boundary? Is this all RB alpha then, the beta alpha then?
So for example, if I run this summation,
Yeah.
okay, so when this is alpha, this is beta, so this is beta.
Yeah.
So I store this information that who all are the neighbors of this alpha. Okay, so this bond length has been taken, I have stored there, this bond length. Similarly, I stored this bond length also while taking the summation of it. Okay, so you see that you counted 2 bonds here.
And these two bond lengths are the same.
These 2 bond lengths are the same, exactly.
So I divided by 2.
That's why divided.
Then I get this, or get rid of this problem across the
Exactly.
Yes.
cells.
Hmm.
But this R AB or BA is different from that R BA within the cell.
So yeah, of course.
That's
of
different.
course.
So this is not that RAB is equal to minus RBA or something. No.
So somehow if you have a material for which you don't know what is the W, then you can use molecular mechanics to get your W. And this was for crystalline materials, of course. If you have an amorphous material, then you have to do something else. But for crystalline materials, you can work in this way. And you see the key thing was when we computed the energy of the deformed crystal, that big E as a function of little x, the nice thing was that the crystal was still periodic, right? So you could use periodicity and only focus on one unit cell to compute the energy. But what if the deformations that you are applying is such that the crystal does not remain periodic? So what would you do? So if the crystal does not remain periodic for the deformations that you are applying, then you will no more be able to find out the energy of a unit cell from which you could get your W, isn't it? And it turns out for our case, for rods, when we apply bending and twisting to a rod, then that periodicity is actually lost. So we cannot use the standard Cauchy bond rule. And that's where we need to have some, so another kind of Cauchy bond rule, which can relate the undeformed lattice vectors to the deformed lattice vectors. Okay. All right. So, that was the motivation for a new Cauchy-Born rule. So, let me give you some more perspective. As Prakhar told you in the beginning, the first question was, what if we do not know W of f for a material? So, that question he has addressed it for crystalline materials, right? If you do not know W of f for a material, you can find it through molecular mechanics. His another question was, what if the rod has lateral dimension of nanoscale? In those situations, it turns out that the energy that we wanted, psi of v comma k, for such nanorods is not just the energy, the bulk energy over the cross section W of f, but it also has got the surface energy. Where this part is the surface energy. Now, the first integration is something you know how to get it, right? But how do you get the second integration? Because this requires that you should know the form of this phi s, surface energy. So, that question has been also addressed, and people use what is called surface Cauchy-Born rule. Just like this Cauchy-Born rule for bulk crystals, for bulk energy, there is something called surface Cauchy-Born rule for surface energy. Okay, so that is how you address the second question. Now, the third question is, what if the nanorod can't be thought of as a continuum, I mean as a 3D continuum. You know, for example, when you have a single walled carbon nanotube, you all must have heard about it, right? Single walled carbon nanotube. So, it is such that its surface is just one atomic layer thick. So, on the surface of the nanotube, it is just one atom, it is a grid of one atom. Now, would you think of it as a 3D continuum? You know, 3D continuum would mean that it has dimensions in all the three directions, but for a nanotube, it does not have any dimension in the along its thickness, it is just one atom, right. So, if it is not a 3D continuum, you can't even define your deformation gradient, and then you won't even, and then you can't think of a 3D strain energy density. So, how do you then get your psi, your rod's strain energy for such bodies? You know, if you think of, let me just draw a schematic of a nanotube. It is really like a thin cylinder, isn't it? It is a thin cylinder, but it is so thin that it has just one atom along the thickness. So, you can't think of it as a continuum, but you may still want to model it as a rod. because even when this nanotube is deforming, you will see some nice examples, of course, later on. Even when this nanotube is deforming, you can always think of a center line of the nanotube and some kind of orientation attached to every point to the center line, which denotes the orientation of the cross section of the nanotube, isn't it? So, you can always think of it as a rod, but it is not a conventional rod, it is not a 3D, it is not a bulk rod. It is such a rod whose thickness is just one atomic layer. So, when you model this atomic structure as a rod, then you will need to know what is the psi, strain energy per unit length, because in your rod equations this comes, and then the question is how to get that psi. And I told you this does not fall in any of these two categories, because it is not a 3D continuum. You can't even define deformation gradient. How do you get W of f? So, this formula does not work. So, you have to think of some direct approach for such cases without recourse to 3D elasticity, because they are not 3D continuum. So, you can't get the energy by thinking it as a 3D continuum and then doing this integration. So, we have to think of some direct approach. Okay. So, that is what we are going to talk about, a direct approach to obtain this energy, and that direct approach would actually work for all the three cases. It will not be just limited to the third case, it will work for all the three cases. Okay. Okay, so a direct molecular approach to obtain psi of v comma k. All right, so what should we do now? So, let us think of your nanorod. So, although it looks like the same picture that we drew for continuum, but you have to now think of it as a nanorod, okay, which is made up of atoms. So, there are atoms everywhere. You can see the atoms. And then if you think of it as a rod, you will have its center line, its cross section deforming. So, it is going to generate V and K everywhere along its arc length, right. So, it is going to generate some V and K along its center line. It will have one V K over here, another V K over there, so you will have one psi over here, another strain energy psi over here, because they have different V and K. But then how do we compute the psi? That is the question. So, just as we did for 3D continuum, what we did for 3D continuum? We subjected the continuum rod to a constant V and K, isn't it? And then we reduced the rod problem to a cross section. In a similar way, we can think of subjecting the nanorod to a constant V and K, to a deformation such that it has same V and K all along. So, it has same bending curvature, same twist, same shear, same axial stretch all along the length of the nanorod. And if that is the case, then And then we have to see, can we then obtain this psi somehow if we subject the nanorod to a constant V and K. See, a nanorod would be such that in its reference state it will be made up of periodic boxes. You know, you can think of it as a periodic box. So you will have one box which is repeating here, another box. So the same box is repeating. Just as in 3D crystal, the box repeats in all the three dimensions, all the three directions, E1, E2, E3. In case of nanorods, in its reference state, that box will only repeat in one direction along its axis, and that you can call its unit cell, something which is repeating along the axis. And many people also call it fundamental domain. Okay, but let us not introduce new terminology, we just call it unit cell. So, this is the simplest repeating unit cell for nanorods. And you see, this nanorod, when it gets deformed, these repeating boxes would be deforming, isn't it? And if you apply constant V and K all along the length of the nanorod, then won't it be that all the boxes will somehow deform in the same manner, isn't it? So, we would actually want to determine the map, which is actually your deformation map, determine the deformation map for the repeating boxes. So, in the reference state, the positions of atoms in the boxes we denote by big X I comma j, where I denotes which box I am talking about. Is this I equal to 0, I equal to 1, I equal to 2, I equal to 3, I equal to 4, and j denotes your atoms within the box. So, if you want to relate this to your 3D crystal, then j are your basis atoms in the box, whereas this I tells you which box. And you see, this I is a scalar here. Over there you had a vector, there were 3 I's, one for each of the directions, but in case of nanorods you have a single I because it is only repeating periodically along the axis.
So the lattice is like one dimensional.
One dimensional, yes. Okay. Maybe I can draw some nice picture also. So, a nanorod, for example, could look something like this, and then you have the boxes. And within each box you may have, let us say, 2 atoms, one circle, one cross. So, it is like a one-dimensional crystal, as Professor Steinman said. So, it is a one-dimensional crystal. So, this J for this particular case runs from 1 to 2. J equal to 1 could mean circle, and J equal to 2 could mean the crossed atom. And then I equal to 0 may be here, I equal to 1 is here, I equal to 2 is here, 3, 4, 5, 6, 7, 8, 9, 10, then minus 1, minus 2, minus 3. So, it can go in all the 2 directions. So, that is for the reference state, but we want to get the deformation map. So, we want to get where do those atoms go after being deformed. So, what is little x of I comma j? So, that is what we want to know. And we would like to get this for a deformation in which the nanorod is subjected to constant V and K. Okay. Determine the deformation map for the repeating boxes for the situation where the nanorod or the one-dimensional crystal is subjected to constant V and K. Can you think of what could be the deformation map? So, here again you can take some hint from the 3D deformation map. Not that one, but the 3D map for a rod, when the continuum rod was subjected to constant V and K. What was the deformation map? Do you guys remember that little x of big X1 comma big X2 comma s, that was equal to little x of f plus e to the power sk times little x of 0, which is the cross section at s equal to 0, x1 comma x2 minus just a second little x of f plus s tau k hat. So, you remember this map? So, we have to take a hint from this map, and maybe we have to find a discrete form of this map which could perhaps work for our one-dimensional crystal. Isn't it? That would be a nice thing to do. You see what is happening here? This is your cross section at s equal to 0, which you translate and rotate along the helix to obtain the cross section at any s. So, somehow you have to do similar thing over here. Maybe you identify a box corresponding to s equal to 0, and that you have to translate and rotate to get the box for any other s. Or you think of a box corresponding to I equal to 0, which you translate and rotate to find out another box corresponding to any I. can you think of what can we do? You know, this thing is like your little x I comma j. J denoting your x1, x2, and I denoting your s. And the thing that you see over here, that's your little x of 0 comma j. That's the box for I equal to 0. Okay, I'll just take 2 more minutes. Maybe Smithy, please don't erase this. I'll just write over here only. I'll just write down the deformation map, and then we continue from there in the next class. So can you think of what could be the best thing to do if you want to discretize this map, if you want to look at a discrete form of this map? See, over there your S is continuous, S. So you find cross section at any S, but in the discrete world the box is an integer, right? It comes after every integer, 0, 1, 2, 3, 4. So this I over here, this I is somehow the discrete analog of that S. When your I becomes 2, what could be the S, for example? I equal to 0 if it corresponds to S equal to 0, and you say I equal to 2. So this is I equal to 0, then I equal to 2. How much have you moved? That would be the S, right? So what do you think? Can we write S equal to I times the length of the box, I times L naught, isn't it? And then everything works magically. Okay. Little x of f plus e to the power I L naught k times little x 0 comma j minus little x of f plus I L naught tau times k hat. So that's the discrete form, discrete analog of that continuous map. So this is the map which you can use to construct your deformed nanorod, which is subjected to constant V and K. And you see here, this is denoting the I equal to 0 box, and this denotes any other box. So maybe we take it from here, all right? So that would be the unknown which you would have to solve for. So earlier we were solving for the warping of S equal to 0 cross section. Now we will solve for the atomic positions in the I equal to 0 box. Okay, so we take it from here in the next class.